In this part of the unit current electricity, you will learn about the points of differences between resistance and specific resistance of the conductor. The resistance of the wire or conductor is directly proportional to its length. Greater will be the length of the conductor, greater will be the number of collisions with other ions and electrons. So resistance will increase. With increase in area of cross section of the conductor, what happens? Let us see. With increase in area of the conductor, there will be less collisions between the electrons and ions. So electrons will pass on easily from one end of the conductor to other end. So the resistance decreases with increase in area. If we combine these two factors, what you get? R is proportional to L by A. Convert it into equality sign, you get R is equal to rho times L by A. What is rho? It is proportionality constant. It is called resistivity or specific resistance of that conductor. What is unit of this resistivity? What is unit of this resistivity? The unit of resistivity is ohm meter. Ohm meter. So it is dependent upon length and area of cross section and nature of the material. Also than this, it depends upon temperature of the conductor also. With increase in temperature, resistance of the conductor increases. Resistance of the conductor increases. So R is dependent upon dimensions of the conductor, length, area of cross section and nature of the material and temperature of the conductor. Now let us see what happens in case of resistivity. Resistivity of the conductor is independent of dimensions of the conductor, means it does not depend upon length and area of cross section of the conductor. This is very important point of difference between rho and R. So specific resistance of a conductor is equal to resistance of a wire of unit length and having unit area of cross section. Now let us find the expression for rho by making use of Ohm's law. We know the relation between current and drift velocity. I is equal to NEA Vd. So we can substitute the value of Vd by making use of drift velocity, where this electric field E is given by V by L, potential drop per unit length. So replacing Vd by the term Vd is equal to EV by ml into tau in above relation I is equal to NEA Vd, what you get? I is equal to NEA EV by ml into tau. So from here we can get V by I. V by I. What will you get? V by I is equal to ml by Ne square A tau. This is resistance. V by I is resistance is equal to m by Ne square tau times L by A. The quantity within the bracket is called resistivity or specific resistance of the material of that conductor. This is called specific resistance, m by Ne square tau. Now how it varies, on what factors it depends, let us see. Rho is equal to m by Ne square tau. In it m is constant, the mass of the electron, E is constant, the charge of the electron. The difference comes because of n, the number of free electrons in per unit volume, and the relaxation time. So the first factor affecting the resistivity of the material is the number density, that is number of free electrons in per unit volume of that conductor. Greater will be the number of free electrons, lesser will be its resistivity. So for an ideal conductor, it is assumed that the number of free electrons is infinite in it. So resistivity must be 0 for an ideal conductor. Similarly, for an ideal insulator, the resistivity will be infinite because the number of free electrons in ideal insulator is assumed to be 0. So second factor affecting the resistivity is temperature. Dependence of resistivity with temperature is given by the relation rho is equal to rho naught times 1 plus alpha T minus T naught, where rho is the resistivity of the material at temperature T and rho naught at the temperature T naught. Alpha is temperature coefficient of resistance. Alpha is equal to, by solving this we get alpha is equal to delta rho by rho naught delta T. So the temperature coefficient of resistivity is defined as the change in resistivity per unit original resistivity per unit change in temperature. Rho is equal to delta rho by rho naught into delta T. So change in resistivity per unit original resistivity per unit change in temperature. Now let us see how resistivity of conductors, insulators and semiconductors vary with rising temperature. In case of conductors and insulators, the alpha is having its a positive value. Why it is having positive value? Because with increase in temperature, relaxation time decreases and there is increase in number density also. But in case of conductors, already there are free electrons in good number. So impact of decrease in relaxation time is more than increase in number of free electrons. So net effect is increase in resistivity of the material with increase in temperature. In case of insulators, there is only a marginal change because there is only a slight change in number density because of rise in temperature. But in case of semiconductor, number of free electrons per unit volume changes drastically with increase in temperature. So there is decrease in resistivity of the material with increase in temperature. Although there will be decrease in relaxation time in case of semiconductor, but the impact of increase in number will be more because the number of free electrons in semiconductors in beginning was very less, that was very small. This is all about this topic. Thank you.